Okay, so good morning today. What we're going to start getting into is the oil nozzle in our oil burners. So really, for oil nozzles to really work correctly, the first thing that we have to make sure is that it's the correct one that's in there. Because if we don't have the correct one in there, we can run into a lot of different problems. You can overfire a furnace, you can mess up the efficiency of the furnace. You can burn out components like the combustion chamber, stuff like that. So making sure that you have the proper size is really the key to making sure that the furnace is running as efficient and as clean as it possibly can. By knowing how to determine the proper firing rate, you have to make sure that you know the right spray angle, you have to know the appropriate spray pattern, and you have to also make sure that the nozzle in the furnace is set up for good and reliable combustion. Okay, so the oil burner nozzle is really nothing more than a precisely engineered product. Manufacturers they are manufactured really to different, very close, different tolerances that are necessary really to atomize and meter the fuel in the spray patterns and angles required for a piece of equipment. And so why is that really important? Well, the spray pattern and the angle of our nozzle and what the oil is going to be shooting out the end of that nozzle is really kind of key to whether or not we're going to burn the oil efficiently. It also is going to depend on the combustion chamber that we are using. Is it like a narrow combustion chamber, or is it an extremely long combustion chamber? So the spray patterns and the angles of it really kind of take a lot and really play a vital role in how the burner actually operates. Okay, nozzles are neither made of stainless steel or a combination of stainless steel and brass, allowing them to withstand the temperatures, pressures, and variety of fuels found in the combustion environments. So really, the nozzle performs three vital functions inside a oil burner. The first thing that it has to do, it has to atomize the oil. Okay, heating oil must be atomized to burn. Although the vaporization is accomplished with heat, the oil first has to be broken down into much tinier droplets first in order for that to happen, and we call that atomization. And that allows the oil to vaporize quickly and evenly for fast and quick ignition. The next thing that it will do, it's going to meter the oil. Okay, the nozzle delivers a fixed amount of atomized fuel to the combustion chamber. The fuel is measured in gallons per hour, or GPH, at 100 pounds of pressure, or 100 psi. Okay, for burning rates below 5 gallons per hour, there are more than 25 different flow rates, each in 6 different spray angles and 6 or more spray patterns. Okay, so that's a little fun fact to actually know about. The last thing that a nozzle is going to do, it is going to pattern the spray. Okay, a nozzle is expected to deliver the fuel to the combustion area in a uniformed spray pattern and angle that is best required or best suited for a specific burner and combustion chamber. Okay, and we're going to get into that a little bit. So a little fun fact here, that before atomization of 1 gallon of fuel oil, it's going to have a surface area of about 180 square inches. After that atomization, 1 gallon of fuel oil is broken down into about 55 billion droplets, and it has a surface area of about 670,000 square inches. So it's a little fun fact for you. That's just how the purpose of that spray and the metering and everything that goes through a nozzle, how it actually is able to expand the surface area of what the oil can actually do. So the effects of pressure on nozzle performance. Well, historically, nozzles and manufacturers have set most of their burners up to about 100 psi. Okay, they considered that really a satisfactory set point for a lot of our burners. Okay, and all nozzle manufacturers calibrate their nozzles at that pressure. So when you're looking at an oil nozzle and you see the numbers that are stamped on the side of it, those numbers are rated at 100 psi. So if I raise or lower the pump pressure on an oil burner, those numbers are not going to be what is on that nozzle. And I'm going to cover that in a minute. Okay, so many burners and appliances, especially like boilers, furnaces, water heaters, all that stuff that uses oil for heating, manufacturers are actually recommending higher pressures for their product. Okay, higher pressures create better atomization. And when we raise the pressure on an oil burner, the oil droplets now become smaller. And when we do that, we create a better burn. We're burning the oil more efficiently, okay, which results in many cases, less soot, less smoke, a better, clean, and efficient burn. Okay, many manufacturers are actually using pump pressures up to about 150 psi. So as we do that, all of these parts inside an oil burner, or an oil nozzle, sorry, is what actually is creating that spray pattern. So oil, typically at about 100 psi, has to come through our little sinister little filter here, okay, which in many ways I like to consider really the last line of defense that's going to protect my orifice on my oil nozzle from getting any sort of dirt and debris to plug it up. Oil shoots through this filter, fills up our little chamber in here, goes through our little tangential slots, and then goes through our swirl chamber. The swirl chamber is what actually creates the pattern and swirling effect. The orifice is what actually produces a correct amount of oil. For example, 0.5 gallons per hour of oil is going to come out of our little orifice. And then we have our spray angle, and that's where our oil is actually going to become atomized and widened so that we can actually have a clean and efficient burn. Over here you can kind of see how that angle actually is occurring as the oil comes shooting out of there. Okay, so how a nozzle works. Well, again, heating oil under typically 100 psi passes through the strainer to remove contamination, then through a set of slots cut at an angle into the swirl chamber. Okay, the angle of the ejected oil creates a high velocity swirl, sort of almost like a tornado. And as the oil swirls against the swirl chamber walls, it creates an area of low pressure in the center. The pressure differential moves the oil out through the orifice in a hollow tube shape where it spreads into a film that stretches until it ruptures into literally billions of tiny droplets. So you can kind of see that over here in this little picture. We got 100 psi of oil. It goes through our little tangential slots. That tangential slots creates a little swirl chamber. That swirl chamber now pushes all that oil out through the orifice and then out into an atomized spray cone. So here you can see in these pictures the difference between pressures. Here it's only at 10 psi, which is very, very little. And you could kind of see how big the oil droplets are, and if you actually could kind of see almost like that swirl pattern going through here. But as we increase the pressure coming out of that nozzle, you can kind of see that those oil droplets now become finer and closer together. Eventually 300 psi, it's relatively full. So as you might expect, pressure increases causes a corresponding increase in the amount of oil flowing through the nozzle. A nozzle rated at 1 gallon per hour at 100 psi will deliver about 1.23 gallons per hour at 150 psi. Okay, so increasing pressure also reduces the size of the droplets in the spray. So for example here, an increase of from 100 to 300 psi reduces the droplets diameter by 28%. Okay, lower pressure means larger droplets that are much harder to vaporize and obviously burn. And that is what causes a lot of your sooting. It is that unburned oil that's going through there that doesn't exactly ignite. So while pressures greater than 100 psi are sometimes desirable, never operate less than 100 psi. That is really important. If you are going to adjust your pump pressure on anything, you really do not want to go any lower than 100 psi. Anything other than that, you're just going to have a lot of issues with the burner and the burner operation. You're going to have a really crappy burn. You're going to be going back and you're going to be punching out that boiler, cleaning that flue pipe, because it's just going to get completely plugged up with soot and crap. So what we can do is we can use what is called a nozzle or a pump pressure chart. So here's an example of a pump pressure chart. Now typically up here we would actually have the nozzle that is inside the burner itself. So like for example, it would probably be like a 0.40 nozzle in here, pump pressure at 100. So we can use this chart here to figure out how much GPH is actually coming out of a nozzle if we raise the pressure above 100 psi. So for example here, if we look, we have a nozzle here at 0.40. Okay, at 0.40, it would, at 100 psi, it would put out 0.40 gallons per hour. But if I raise the pump pressure up to, say, 125, if I'm pushing 125 psi through my nozzle, I'm not going to be putting out 0.40 gallons per hour. I'm going to put out 0.45 gallons per hour. Or if I bump it up to 200 psi, I'm going to put out 0.57 gallons per hour. Now, why is this important to know? Well, there's going to come a time when you're out in the field and you may not necessarily have the correct GPH nozzle on your truck. Okay, nozzle may have to be, we'll say it's a 0.5 gallon per hour nozzle, but you don't have a 0.5 on your truck because you ran out. You used the one on the last call. You can use a different gallon per hour nozzle. You just have to adjust the pump pressure to get the correct GPH. Obviously, you want to make sure that you have the correct spray angle, okay, because you don't want that to be wrong. You want that to be correct. But if it's not the correct gallons per hour, you can use a different nozzle. You just have to adjust the pump pressure. So, for example here, say we had a unit that had a 0.60 gallon per hour nozzle in there. We didn't have one. Which one can we use? We can use a 0.50 gallon per hour nozzle. All we would have to do is adjust the pump pressure to 145 psi, and that 0.50 gallon per hour nozzle will give us 0.60 gallons per hour as we would actually require. So you can see that there. See, it's a 0.60 right there. But if I want to get it, I can use a 0.5 and just bump the pressure up to 0.45 to 145 psi, and there you go. I'm at 0.6 gallons per hour. That nozzle will actually work. So your spray patterns, they are in different classifications. They are generally solid, hollow, or what we would consider semi-hollow. Okay, hollow cones, as the name implies, the greatest concentration of droplets is at the outer edge of the spray with little or no distribution in the center. Generally, hollow cones are used on low firing rate burners, particularly those that are less than a gallon per hour. This is an important advantage in fractional gallonage nozzles, such as those used in mobile homes, where cold, high viscosity oil may cause a reduction in spray angle and increases the droplet size. Hollow flames also tend to be much quieter when they actually do ignite. Your solid cones, here the distribution of droplets is more uniform throughout the pattern. These nozzles work best when the air pattern of the burner is heavy in the center or where long fires are required. They provide smoother ignition for burners firing over 2 gallons per hour. So that's really kind of where you're going to see your solid cone type nozzles, is if you are dealing with 2 gallons or more. An interesting characteristic of solid cone patterns is that they become more and more hollow as the flow rate increases, particularly above 8 gallons per hour. So in these types of nozzles, the more I bump the pressure up, they actually intend to become more of like a hollow pattern instead of a solid. In addition, increased pump pressure tends to make both the hollow and the solid patterns more hollow. Okay, your semi-solids, many burners perform well with solid or hollow spray patterns. To accommodate these designs, nozzle manufacturers have developed patterns that are a compromise between both, and we consider those semi-solids. So your job, basically as a technician, is to select the correct nozzle that puts the oil spray where the oil velocity delivered by the burner is the greatest. Okay, in most modern equipment, the appliance manufacturer designates the nozzle to use. Where do we find that information? It's going to be with the literature. It's going to be on the nameplate of the piece of equipment that you're working on. So here's a nice reference chart that I like to say when it comes to different manufacturers and their spray patterns. Now, these manufacturers will use different letter designations to signify what type of spray pattern they have. So, for example, see Danfoss here, for a hollow pattern spray nozzle, they use the letter designations of AH. But a Delvin uses A for a hollow. Hago uses H. Monarch uses NS, and Steinman uses H. So what is really important is if you have to interchange your different nozzles for whatever reason, you have to make sure you know the letter designations for the spray pattern. If you have a Danfoss hollow pattern nozzle and you have in the burner, but on your truck you have a Delvin, you have to make sure that you're using an A pattern nozzle, because hollow is what is being used. Danfoss, Delvin is your A. Okay, nozzles can be interchanged. You don't have to always go with one particular manufacturer. You can use different nozzles. Okay, spray angles. These refer to the angle of the cone of spray from the nozzle. Spray angles are available from anywhere between 30 to about 90-degree angles to meet the wide variety of burner air patterns and combustion chamber shapes. Generally, round or square chambers are fired with about 70 to 90 degree nozzles. Short, wide chambers need a short, flat flame. Long and narrow chambers usually require a 30 to 70 degree solid cone nozzle. So here you go. So if you have a smaller combustion chamber, you're going to go with a much wider angle nozzle. If it's a kind of a long and narrow one, you're going to kind of go with the smaller, 30 to about 70. And this illustration over here just kind of gives you the reference of your different angles. Obviously 90 degrees is very, very wide, and 30 degrees is kind of shoots the oil in a much longer spray pattern. The spray pattern and angle must be such that all the droplets burn completely in suspension in the combustion area. Unburned oil must not strike or what we would consider impinge on any cold surface such as the chamber walls or floors, the crown sheet of the heat exchanger, or the burner end cones. Impingement of unburned droplets will cause high smoke and will lead to future service calls. Okay, that is really important to know. You don't want to have impingement because you're going to destroy stuff. Okay, the correct spray pattern and angle depends on the air and oil mixing design of the burner and the shape of the combustion chamber. Okay, your flow rates, atomizing nozzles are available in a wide range of flow rates. Okay, generally with hydronic and warm air heating system, the smallest firing rate that will adequately heat the building on the coldest day of the year is the proper size to use. Another guideline is to select a flow rate that provides a reasonable net stack temperature regardless of the connected load. Okay, this avoids acid condensing in the stack, which occurs when your stack temperature is about 150 to about 200 degrees. And when we get into combustion efficiency, we will cover that a little bit more as to why net stack temperature is really important when it comes to the burning of our fuels. Okay, the nozzle that is too small will not produce adequate heat or hot water. A nozzle that is too large will cause the unit to short cycle. It's going to reduce the efficiency of that furnace, and you're obviously going to be wasting oil. So whenever it is possible, determine the manufacturer's recommendations on nozzle selections and never overfire the rating of a heating appliance. Dual filtration nozzles. There are what we call dual filtration nozzles that are out there. And these are going to be used on your mobile home installations and other units with very low firing rates. So in addition to a standard nozzle filter, these nozzles have a secondary internal filter located immediately before the metering slots, and the extra filter gives the nozzle 35% more nozzle filtration. The internal filter does not change the nozzle performance, it just increases its longevity. Okay, burner air patterns. Burner air patterns are much like nozzle spray patterns in that they fall with solid and hollow classifications. Your burners with solid air patterns are often referred to as open-end burners. There is no restrictive air cone and in the end of the air tube to direct the air efficiently or effectively in a desired pattern, and this produces high velocity air down the middle of the air tube and works best with a solid nozzle or narrow spray angle. This situation does not apply to your flame retention burners. Flame retention burners, on the other hand, are equipped with air handling devices in the air tube that afford better mixing of air and oil vapor in the combustion area. Many flame retention burners can fire both solid and hollow nozzles with good results because of the strong recirculation pattern that they produce. And in flame retention burners, the flame front is held very near to the burner head. It creates a flame that is less likely to pulsate or produce soot. Okay, nozzle selection of these burners should follow manufacturer's recommendations and follow general guidelines. Okay, for example, burners with flow rates up to 2 gallons per hour. Hollow nozzles can be used successfully for most applications, even on burners with most of the air down the middle. Hollow nozzles in lower firing rates produce the quietest operation. It is often better, especially in furnaces, to sacrifice 1 or 2 points in efficiency for a quieter operation. Okay, burners with flow rates between 2 and 3 gallons. You may use a hollow or solid nozzle depending upon the burner's air pattern. At this higher firing rate, spray patterns are not as critical. With burners that are firing above 3 gallons per hour, here it is advisable to standardize a solid nozzle which produces smoother ignition in most burners. Burners with hollow air patterns are the exception, so obviously you're going to want to check with your manufacturers and what they recommend. So can nozzles be interchanged? Yes, absolutely. Okay, replacing nozzles with one brand with those of another can sometimes present a problem, though, but they can be interchanged. There are subtle differences between manufacturers because they use different methods of production and evaluation. Okay, the burner manufacturer tests their burners in different appliances and determine what type nozzle from which nozzle manufacturer works best in that appliance. Okay, burner manufacturers publish nozzle recommendations called OEM specifications. You can actually get one of these guides and keep it on hand because it basically can tell you what nozzle works best with what type of burner and what type of appliance. If you are working on a unit not listed in the specification guide, you will find that generally all hollow nozzles have similar spray patterns and may be interchangeable. The variation shows up mainly in the solid nozzles, and if you must change brands, you will have to do the same testing to determine the best nozzle for that application. If you can get a hold of a nozzle interchange chart, obviously it'll help you out. Okay, nozzles, when it comes to care and servicing these guys, you are never, under any conditions, interchange the inner parts of a nozzle with those of another nozzle. Now, each nozzle component is matched exactly to all the other components of that nozzle. In fact, you should leave a nozzle in its original container until you are ready to install it. You should store all your nozzles in a proper nozzle case. They are available from nozzle manufacturers. Handle nozzles carefully. Pick them up by the hex flats only. Do not touch the filter. Do not touch that strainer. Do not touch the orifice. Okay, even clean hands have enough dirt on them to plug up the tiny slots inside the nozzle. Only install nozzles with clean tools to reduce the possibility of contamination. If possible, use a nozzle changer or a nozzle wrench when changing a nozzle. Before installing a new nozzle, flush out the nozzle line and adapter with clean oil or a solvent. Before you install the nozzle in an adapter, be sure the inside of the adapter is clean and free of carbon and contamination. Do not put anything on the nozzle threads. Screw the nozzle into the adapter 1/8 to 1/4 turn past hand tight. The nozzle orifice face is polished to a mirror finish. Do not ruin it with a wire or a pin or by bumping it with a wrench. Okay, that will ruin the spray pattern. If a nozzle is dirty or plugged, simply change it. A good quality nozzle should last at least 2 heating seasons. Nozzles should not be very hot when operating because of the amount of air and fuel traveling past them. Nozzles overheat from pour or over the fire draft. Over the fire draft should be at least -0.01 inches to keep the nozzle cool. There are some exceptions to this rule, and we'll cover that when we get into combustion efficiency. Manufacturer's instructions take precedence over everything. Be sure the end of the burner air tube does not extend into the chamber. The face of the end tube should be flush with the face of the chamber or recessed about 1/4 inch. Okay, your air and fuel mix and flame pattern. What constitutes a perfect oil burner flame? Well, that's a question that everybody likes to ask. When it comes to burning of a fuel, there really is no such thing as a perfect combustion. There's always going to be something in there that's going to be unburned. Okay, what our name of the game is basically trying to burn as much of the fuel as best as possible. So theoretically, each droplet of oil that leaves the nozzle orifice should be surrounded by air. It should be vaporized and then burst into flames and totally burning all the hydrogen and carbon atoms in the fuel. Okay, that's perfect combustion. This air volume generated by the burner fan, and in most applications aided by the draft over the fire, should be adjusted to deliver the exact amount of air required by the fuel being fed through the nozzle. It is impossible to reach this perfect state in the field, but it is a good target to obviously shoot for. That's basically the name of the game. Okay, is to get this perfect air and oil match. The closer you get it, the cleaner, the quieter, and the more efficient and odor-free the flame is actually going to be. There are 6 elements for the perfect air-oil match, okay? And that's your air volume, your oil pressure, your spray pattern, your oil spray angle, and the air pattern of the burner. The air pattern of the burner is the most important factor out of all of this. This is unfortunate because you cannot control or adjust air patterns. It is fixed by the burner design. Also, you cannot see the burner air pattern. You must rely on trial and error on your quest for that perfection of that air and oil mixture. Okay, your tool in your search for the perfect flame are using a smoke tester. You're going to use a stack thermometer, a draft gauge, a pressure gauge, a CO2 or O2 tester, and the manufacturer's recommendations and the experience of the person who was there before you. The best burner adjustment is one that allows a smokeless, sootless operation with a minimum of excess air. Okay, as you can see in these types of diagrams, if I have too much oil coming out and not enough air, as you can see, I'm going to have unburned oil. Okay, wide spray angle, that's no good. Okay, if I have too much air and not enough oil, it's going to be too rich. I'm going to have a problem. I have to manage my air and my fuel pattern to get that correct burn. Okay, effects of viscosity on a nozzle performance. One of the most important factors affecting nozzle performance is the viscosity of the fuel. Viscosity is the resistance to flow, the thickness of the oil. It is harder to light cold oil, so ignition is delayed. And if the viscosity is too high, the flame out, and there is no heat is going to be the result. The effects of increased viscosity can be confusing. As the viscosity of the oil flowing through the nozzle increases, so does the flow rate. At high viscosity, oil passes into a nozzle through the tangential slots and into the swirl chamber. The rotational viscosity actually will slow down. And as that results, the walls of the tube of oil leaving the nozzle orifice is actually thicker. More oil enters the chamber and the droplets are actually bigger. The easiest way to cut down on the effects of cold oil is to increase your pump pressure. Another solution to cold oil is to install a nozzle line preheater. Okay, this simple strap-on device increases the temperature of the oil arriving at the nozzle to about 100 to 120 degrees. The nozzle line heater is wired in parallel with the limit control, so it is energized whenever there is power to the heating system. Okay, nozzle after drip. The quickest way to set up a heat exchanger is nozzle after drip. This happens when oil drips from the nozzle orifice after the burner shuts down. If the combustion area is still hot, the oil burns into a smoky fire. If the combustion area is not hot enough, the oil drips out and collects at the bottom of the chamber. When the burner comes back on, all this extra oil lights and results in smoke, soot, and the furnace is going to rumble. There are three basic causes of after drip. First one is a defective oil pump shutoff valve. You are also going to have air entrapment in the nozzle lines, or oil expansion in the nozzle line caused by excessive radiant heat at shutdown. So if air is trapped in the nozzle line or adapter, it will cause after drip. A bubble or trapped air will be compressed to about 1/7 its original volume by the 100 psi pressure from the oil pump. So when the burner shuts down, the pressure eases back to normal, and the air bubble then expands back to its original volume. That rapid expansion pushes out the oil in the nozzle, causing an after drip for several seconds. Okay, as you can kind of see here. As we're pumping oil through, that compression and that pressure is going to cause those air bubbles to compress into smaller areas. As that pump shuts down, those air bubbles are going to expand back to their normal size. And when that happens, it's going to push all that oil that is inside that nozzle line out of the orifice or out of the nozzle and then into the chamber. This can lead to delayed ignition, sooted up heat exchangers, and obviously the smell of oil or fumes. This condition is diagnosed by looking into the chamber at the burner shutdown. Okay, what you can do to do that is you can actually take like an inspection mirror and kind of look inside the chamber to see whether or not you have any after drip. Expansion of the oil in the lines can cause after drip. For every degree Fahrenheit of temperature rise, there is a 0.04% expansion of volume. After drip occurs when the burner shuts down and the temperature of the oil in the nozzle line and adapter rise because of the heat of the appliance. And that's nozzles.